Assuming a frictionless spinner and a fluid with zero viscosity, and from the geometry of the system, this assumption relates the spinner blade velocity to the fluid velocity from this equation. This equation is, of course, for the ideal case, for frictionless spinner and fluid with zero viscosity. Of course, in the real case, spinners aren't frictionless and the fluids have finite viscosity. Considering these effects separately, first, considering the effect of friction of the blades. Spinner friction causes the frequency response to be of the form as shown in this equation, where Ft is a retarding torque. Thus, spinner friction adds another term to the ideal response equation, this term, which is subtracted from the ideal response. Thus, if the retarding torque, Ft, is sufficiently large, this second term would be significant, and the spinner frequency response will not be linear with the fluid velocity. The effect of fluid viscosity also reduces the frequency response, as shown here. The viscosity effects, also called Reynolds number effects, and yields a frequency response of the form of this equation. Here, another term is subtracted from the ideal response equation, this term. The effect of fluid viscosity, like the effect of mechanical friction, reduces the frequency response and introduces a nonlinear dependence on fluid velocity, as shown here. These effects are most predominant at low fluid velocities. Here, the combined effect of fluid viscosity and the friction effect of spinner blades is introduced. Here, the first equation, we only subtract the effect of retarding torque from spinner blade friction. The second equation introduces the effect of fluid viscosity, and here the term of viscosity is subtracted from the ideal response. The combined effect is shown here in this equation, where both the effect of fluid viscosity and spinner friction is subtracted from the ideal response equation. In this plot, we compare the ideal spinner frequency response with that observed with mechanical friction and with viscous and mechanical effects. The blue line is for the ideal case, and the first line after the blue line is for the spinner with bearing friction only. And the two last lines are for the effects of both mechanical friction and fluid viscosity. At higher flow rates, these effects reduce the spinner response. However, this response is nearly linear with fluid velocity, with about the same slope as in the ideal case. So in real case, the combining effect of the spinner friction effect and the fluid viscosity appears as shown in this nonlinear equation. And the nonlinearity appears most often at low fluid velocities. However, at high fluid velocities, the response is nearly linear with about the same slope as the ideal case.